Now we're going to switch to inference for population mean. We did inference for population proportion before, because you can do inference for many things. We're going to do 3 of them in this course. So just because you did the inference and the hypothesis test, right, you got your confidence interval, you still actually might be wrong, right? Because you could get a type 1 or a type 2 error, which is a false positive and a false negative. They're referred to as type 1 and type 2 in statistics, basically. So you might think, oh, there's only 2 possible outcomes. Either I got it right or wrong. And that's not actually the case. So depending on your significance level, you could get 1 of 2 errors, basically. So depending on when you set your alpha. So you could reject, right, or not reject the null hypothesis. And based on that, there are 2 possible outcomes each, right? Because if you reject it and it was true, that's a problem, right? If you reject it and it was false, that's what should happen. That's okay. Excuse me. If you don't reject the null hypothesis and it's true, that's what should happen, right? It was true. But if you don't reject it and it was false, then that is an error, basically. So typically they consider this decision 1, type 2, type 3, and type 4. At least in the American textbooks, it varies as far as the order, how they set this up, because they can always obviously change the x and y axis orders. And of course, these are the 4 outcomes here, where 2 are correct and 2 are not correct, essentially. So there are 4 possible outcomes in inference that can actually happen. So let's take an example of a court case. So in a court case, you have to assume that they're innocent, right? And if enough evidence is found, they are not innocent. Otherwise, the alternative is guilty, right? So defendant is innocent and will be convicted at trial. Ooh, that's not good. If you're innocent, why would you be convicted, right? So that's an error, isn't it? That's a type 1 error, right? So that's a false positive, otherwise known as a type 1. Okay. The defendant is guilty and will be convicted at trial. Okay, so that would be this one here, right? Because what do we do? Is the defendant is guilty, right? So we convicted, didn't we? We rejected the null hypothesis. Okay, the defendant is innocent and will be acquitted at trial. Well, that's good, right? That's a decision type 3. Okay, and the defendant is guilty and will be acquitted at trial. Oh, but they're guilty. You didn't find them. Well, I guess the prosecution screwed up there. That's a type 2 error, right? So that covers all of your possible outcomes that could happen for this, essentially, right? Looks like I got an extra thing there. All right. Anyways, let's try this one here. Let's put example. When you bring your car in for 5,000 miles service, there are 4 possible outcomes, which can be related to the hypothesis testing situation here. Okay, your car is either broken or it's not. The dealership does additional repairs or it doesn't. So basically, does your oil change, tire rotation, and the question is, does it do extra repairs or not based on it being broken? So one of 2 things will happen here. So if I get my on the right page here, so we have to assume the car is not broken. Right, that is the assumption, kind of like you are innocent is the original assumption, correct? Okay, and format color blue. So we'll copy that. So if enough evidence is found, then it is broken, right? Which is what happens in inference, right? So scenario 1 would essentially be the car is not in need of additional repairs, and the dealership does additional repairs. Well, that's not good. So that would be a false positive, right? Okay, let's do blue, bold and blue. We'll copy it. We'll put this down here. So the car needs additional repairs, right? And the dealership does additional repairs. That is good. That's what should happen, correct? Okay. is in need of additional repairs. There we go. I like that better. Okay, so then we have is not in need of additional repairs, and the dealership does not do additional repairs. That's what should happen, right? That's type 3. Okay, and lastly, the car is in need of additional repairs, and the dealership does not do additional repairs. That's a false negative. They didn't find the actual problem, correct? Right? So if we draw the picture, let's see how well I can do this with the freehand here. Right? So make a box, right? Make a box. Oh boy, that's not a very good box, huh? So we have decision type 1, type 2, type 3, type 4, right? So this is the correct decision, right? This is the correct decision. You can write the whole word in there if you want. This is a type 1 error. This is a type 2 error, right? Because what do we do? We rejected the null hypothesis here, and we do not reject the null hypothesis here, correct? Okay, so either the null hypothesis is true, right? True. Or the null hypothesis is false, right? Okay. So basically, if you're rejecting it, that means you're going to fix it, right? And if you do not reject, that means you are do not fix, right? Do not fix. And the problem is, if the null hypothesis is false, that means it's broken, right? This means it's broken. And this means it's not broken, correct? Not broken. So it being broken or not broken relates to either you fixed it or didn't fix it, which gives us our 4 outcomes essentially. 2 of them are good outcomes, 2 of them are bad outcomes, right? But it all relates back to this error box, we'll call it. Okay. All right. So you have the probabilities of alpha and beta. So alpha is the probability of a type 1 error, and beta is the probability of a type 2 error, basically. Probably rejecting the null hypothesis when it's true. We're probably rejecting the null hypothesis when it's false, essentially, which is the general problems. So they do relate to each other, essentially, depending on your significance level alpha, right? It's going to increase or decrease one versus the other. They do play with each other. You can't eliminate either one of them, right? There's always a chance based on the significance level of one type or the other, essentially. So let's say we have the blood culture contains no traces of pathogen is the null hypothesis. So the alternative would contain, correct? So a type 1 error, right, would be a false positive, which means you detect it when it's not there, correct? A type 2 would be a false negative, which means it's not there and you do detect it, correct? So those are both problems. So when you do each of these, they should be probabilities for alpha and beta. So alpha is the probability of type 1, right? So that's the probability of detecting the pathogen when it's not there. And beta is the probability of a type 2, which is the probability of detecting it when it is there, not detecting it when it is there. So those are both problems, and this is the probability of those problems happening. And again, you never get rid of alpha and beta because there is an overlap here. It's just kind of a sliding scale based on the changing value of alpha, basically. It never really goes away. Okay. Let's say that in a certain experimental drug is a cure rate of at least 75% for males with prostate cancer, determined a type 1 and type 2 error. So I wanted to do one that was an inequality one. So the researcher testing the claims finds the cure rate for the drug is less than 75% when it is actually at least 75%, right? So that's a problem. You didn't come up with what it's supposed to be, right? Conversely, I don't know if it's conversely, but the researcher testing the claim finds the cure rate for the drug to be at least 75% when it has a cure rate of less than 75%. Okay, so I want to do one where it's not always just black or white, on or off, has it or doesn't have it. This is a non-binary type example, basically, right? So, but there's still errors either way of type 1 and type 2, which is what should not have happened, essentially. Okay? All right, so let's look at another scenario here. So the null hypothesis here is the percent of adults with jobs is at least 88%. Okay? So you reject the null hypothesis of the adults who have jobs is at least 88% when it's actually less than 88%. So that's not good, right? So you didn't reject it, and it turns out you're wrong, so that's a type 2 error, isn't it? Right? False negative. Okay. So you do not reject the null hypothesis, right? Okay. But it's at least 88% when it's actually at least 80%. So that's the correct decision. So that's the bottom one, right? Because it's the do not reject. So that's the correct decision 3 on the box, isn't it? Correct? Right? Because you think about it, as far as the box goes, that's the bottom down here. Didn't reject it, and you end up being true. So that's the correct decision, right? Okay. All right. So you reject the null hypothesis. The percent of adults who have jobs is at least 88% when the percentage is actually less than 88%. So that's wrong, right? So that's less. That's you rejected it. So that's a type 1 error, right? Because it's a false positive, right? And you reject again, but it's actually correct. That's just the correct decision 2, basically. So I just copy this one. Okay. Correct decision 2. So you think about it, if you reject, right, if you reject, you're going to be the top part. If you don't reject, you're going to be the bottom part. So not rejecting is a type 2 or correct. Rejecting is a type 1 or correct, basically. All right. And you can look at the math here, too, as far as them being related. So whatever alpha is. Okay. Oh, come on, Al. Come on, pen. All right. That's going to relate here to the correct decision. Whatever, and then beta is going to relate to this decision. Basically, they go hand in hand, essentially, as far as the math goes. Okay. Statistical power. So if you see a lot of the books, like they just say power, which is confusing because power is something different than statistical power. Obviously, when you work with physics, you deal with power, which is not the same thing. So we're not talking about the power, we're talking about statistical power. So essentially, when you choose an alpha, okay, what are you actually doing? You're essentially setting the type 1 to alpha, essentially. So type 1 is the alpha, basically. So alpha is the probability of a type 1. So what you'll notice in a lot of the problems is they'll use alpha, right, is 0.05. That's known as the Fisher rule from a statistician named Fisher, because he said 1/20th is a good value. So since him in the 1700s, the people have used that as the default one, if not specified, right, for alpha. Because simply he said that, and it seemed like a good value, and it relatively is. But and for stats 1, if they don't give it to you, that's a good enough level. And stats 2 and on, they'll specify different alphas and reasons why, but it's good enough for now. Okay. So type 2 is dealing with beta, essentially, right? So if you want to reduce type 2, then you can, increase the sample size, change the significance level, and the effect size, which is the true proportion is farther away from the null. But here's the thing: just because I change the alpha, right? That's if I increase it or decrease it, that will help me with type 1 if I change it, right? But the problem is if I increase it or decrease it, it's going to affect one versus the other. So essentially, if you reduce the probability of a type 1 error, what is the probability of a type 2 error? If you reduce the probability of a type 2 error, what is the probability of a type 1 error? Well, it's an overlap here, right? So if I just reduce this one by sliding this line over, right? Right? It's just going to increase B, and likewise if I go the other way. So these are related essentially. You're not going to completely get rid of it. So let's say I want to decrease B, right? That's going to change the line and increase A, right? So if I decrease A, that's going to increase B. So you're not going to win that battle of changing an alpha to, get rid of one type of error versus the other. You're just making one of the other ones more likely, essentially. So that's statistically essentially how it works. So okay, so that's the end of that as far as those go.